Welcome back to the last session of the day. Those demos, by the way, were fantastic. At least one of them will be out there for the reception, so please enjoy those when you're out there. So this next session is Lunar Surface Science. Leading this discussion is Joel Kearns, Deputy Associate Administrator for Exploration at NASA. Let's give him a warm welcome, Joel.
Thank you, Jim. Let me introduce the members of the panel on lunar surface science. First, we have to my right, Dan Hendrickson, who's Vice President of Business Development at Astrobotic Technologies of Pittsburgh, Pennsylvania. To Dan's right is Susan Lederer, space scientist at NASA Johnson Space Center in Houston, Texas. I'll point out that Susan was project scientist for one of the first commercial lunar payload services landings. As part of that responsibility, she coordinated all the NASA experiments on that commercial mission to maximize science and technology demonstration value for NASA. And to Susan's right is Trent Martin, Senior Vice President of Space Systems, Lunar Payload and Data Services Program Manager at Intuitive Machines of Houston, Texas. So the United States and its partners are going to the surface of the moon. Some people say going back to the moon, but we're actually going to places on the moon that no one has visited before, either with human explorers or robots. There's an image behind us of an area of great interest at the south pole of the moon, what's called the connecting ridge between Shackleton Crater and Décollage. And I think what's interesting about this image is that if you compare it to the images we all hold from the 60s and 70s of the Apollo explorers, when the Apollo explorers were on the moon, they were at the equatorial areas on the mares. The sun was high overhead, the earth was high overhead, and everything looked all lit up, and it was very clear to look around and see. When we go to the south pole of the moon, we're going to be going to places which some areas have light a good bit of the time, some areas are permanently dark and shadowed, and some areas are dark most of the time, and the astronauts and our robots are going to be able to look to the horizon and see bright areas and dark areas, and probably want to make sure that they can walk their way safely from a light area to a light area. There's been a lot of planning taking place to get ready to send robotic and human explorers to the surface of the moon to do scientific and other technological investigations. And a lot of this ties back to NASA's development of what are called the Moon to Mars objectives and the human spaceflight architecture that's aligned to them. To show you why it is we're going, we always talk about the benefits to humanity of our human and robotic exploration efforts. One benefit is science. We want to be able to use our ability to go explore other worlds to answer basic and important scientific questions. In the case of the moon, could be things of the moon itself, or how the Earth was formed, or how the terrestrial planets were formed in our solar system. But in addition to science, we also go to display a certain national posture, either from the point of view of being a leader in the United States or wanting to work very closely with our friends and partners around the world. Sometimes national posture is not just intergovernmental relations, but it's growing and engendering, for example, the private sector to be able to take a bigger and bigger role in space exploration. And also it's for inspiration. There are many people and cultures which are greatly inspired by these very strenuous things we do, whether it's space or other arenas, but there's also great inspiration from going into the unknown, personally making those first discoveries, looking over that horizon and seeing for the first time what is there. And the area that we're going to be focusing on in the short term for exploring our nearest neighbor, the moon, is the South Pole. I've got here an image of the far side of the moon. This is the side we can't see from looking up when there's a full moon in the sky from Earth. And on the bottom is the South Pole. And we will be doing many studies at the South Pole, both for science and for technology demonstration, for engineering, for setting up a camp of explorers at the South Pole. But I'm looking here at the far side and studying from the near side of Earth because there are many other investigations, particularly scientific investigations, that will be done on the far side of the moon. What I'm going to do is turn this over now to to Dan Hendrickson of Astrobotic. But before Dan starts, I do want to mention that Commercial Lunar Payload Services has started flying after many years of preparation. We had our first 2 Commercial Lunar Payload Services missions in January and February this year. We have 2 more coming up later this year. There is a lot of progress on preparing our Artemis architecture to send human explorers to the moon. Not only getting the vehicles together, but also assigning the scientists, the scientific investigations, and the science teams to get ready to go to the moon with Artemis. And I want to remind you that Artemis 3 is the first mission that'll go to the surface, but of course we have Artemis 2 going out to circumlunar voyage in the next years, and then it'll be followed by many more Artemis missions after that and other systems such as the Lunar Terrain Vehicle, which will enable our explorers to go further around the moon. With that, I'll turn this over and the clicker to Dan. Dan.
Thank you, Joel. And thanks to AAS for inviting us to be here today. It's great to be here. As mentioned, my name is Dan Hendrickson. I'm with Astrobotic. We're a space robotics company based in Pittsburgh, but we also have a location in Mojave, California. We were founded back in 2007 with the primary charge to make the moon accessible to the world. And to that end, we flew our first mission. This is the Peregrine lunar lander that you see here on the screen. This is the vehicle in our clean room before launch. It was integrated with 20 customers who had 16 payloads on board, 7 nations represented in some form, whether company, government, university, or nonprofit. We launched on January 8th. It was a perfect injection on board for our the ULA Vulcan Centaur launch vehicle. We got a perfect injection that we were looking for. About 7 hours into the mission, we did encounter a significant anomaly. We had a valve failure, it seems, in which a rush of helium from the propellant tank went into the oxidizer tank and caused a rupture. Which unfortunately at the moment that occurred, we realized that we were no longer going to be able to land on the moon. But we pivoted and had a set of new mission objectives. So the first set of objectives was to get as much data as possible from the vehicle, with the idea of trying to understand the root cause of the anomaly itself, but also to learn for future lander missions that we're planning and to obtain absolutely as much data on the systems that many of them outside of the propulsion system and the anomaly actually worked fairly well, and we wanted to get a lot of the high TRL data coming back from the vehicle. The second set of objectives was to turn on the mission's payloads. So we had, again, a full collection of different payloads that were on board. We had 10 that were active, meaning that they had power and communication planned for their mission. The others were passive. And so those 10, we activated, turned them all on. The vehicle was quickly stabilized by the team in Mission Control in Pittsburgh. Initially, we thought we had probably about 6 hours of life left in the vehicle when the anomaly occurred. We ended up extending the vehicle lifetime to 10 days. So it proceeded on its trajectory out toward lunar distance, which was the original flight plan. Once we reached lunar distance, we made the determination that the anomaly from the burst oxidizer tank and the subsequent leak coming from that was putting the vehicle on an Earth intercept course. The original flight plan had the vehicle going around the Earth, and then we would do a maneuver, slingshot around Earth, and then go back out to meet the moon where it was. Given the anomalous behavior of the propulsion system, we made the really difficult decision to keep it on an Earth intercept course, not wanting to risk a debris event out in cislunar space. We recognized that our mission was one of the early commercial missions going out to cislunar space. So we wanted to set good behavioral norms for the future and ensure the sustainability of the cislunar space environment. And so we decided not to fire those engines out at cislunar space, and then kept it on a controlled reentry over the Pacific, where eventually Peregrine's mission ended after those 10 days. But as I mentioned, we got a considerable amount of data from the payloads. In fact, from what we're seeing and hearing from the payload teams, several of the instruments actually were able to get what looks like probably publishable science. So it's been a really remarkable journey in that when we shifted to that new set of objectives, we were able to still get some valuable science that it sounds like may even inform future Artemis missions on the cislunar environment. So for instance, getting radiation data from the transit of Peregrine. So we have, since the mission concluded, stood up a failure review board. We have an independent chairman who is outside of the company who is chairing that FRB. We are also having that review board be chaired, or excuse me, have members from the NASA community as well as other non-astrobotic folks that are working through the data and getting to root cause ultimately. They're making really good progress. As I mentioned, we believed it was a valve issue and a valve failure, but we are working very hard to get to root cause, which will then inform corrective actions that we will take for our next lander mission, which is Griffin. I went the wrong direction. There we go. So Griffin is the next vehicle and the next mission. So we are taking the data, as I mentioned, from Peregrine and learning a lot and looking to apply the lessons learned and corrective actions to Griffin, which is incredibly important because it's carrying the NASA Viper rover and it'll do so carrying it to the South Pole region, to Nobile Crater, an incredibly important, nationally important, I would argue, mission for the future of living and working on the moon ultimately. And so we take that very seriously, and we are putting all of our company's focus, particularly on the lander team, for the successful delivery of Viper with our Griffin mission. So that's a quick look on our lander delivery missions and the science and the enabling science that we believe we'll get from those missions. Just a quick snapshot looking to the medium term and long term. We're starting with lunar delivery, and that is our primary set of missions and work that we're doing right now at Astrobotic. But we're thinking about the future with our advanced programs group, and they are working on establishing lunar infrastructure and more specifically lunar power, and providing lunar power generation and distribution systems in the form of a program called LunaGrid, which will be a solar-based power system we're looking to set up at the south pole of the moon using vertical solar arrays that are already under development under a NASA STMD contract, and then complementing that with our Cube rover program, which would be essentially serve as a mobile power plug coming out from those VSAT towers. And so this is what's on the horizon. So we're not going to be just satisfied with one lunar day lander delivery missions to return science. Ultimately, we want to break the paradigm and have missions that survive the lunar night and ultimately thrive ultimately indefinitely. And we really believe that power is the future to do so. So this is a quick snapshot of the future of what we're working on. But again, in the near to medium term, we're laser focused on the successful delivery of the Viper mission with our Griffin mission. Thanks very much.
My name is Susan Lederer, and I have had the honor and privilege to work with a number of different payload teams. I've also had the privilege of working both as a support project scientist for the Peregrine 1 mission, as well as the lead project scientist for the first Intuitive Machines mission. So what I would like to do, if I can get the clicker to respond to me, is to talk a little bit about the different manifests that we have so that you have a feel for what kind of science it is that we're doing on board these different landers. When I started trying to figure out how exactly I was going to talk about what it is that we do for science for CLIPS, it's a real challenge to do that because we have dozens of instruments doing, in some cases, suites of science, and in some cases, individual science objectives that they are gearing toward. And so by showing you a number of the different manifests, it can at least give you a feel. So with CLIPS, as I'm sure that you're all aware, we have quite a number of landers. We have 8 task orders that had been awarded to vendors, 2 that have flown so far this year, and as Joel mentioned, 2 more that are launching later on this year. The first that launched, as Dan mentioned a moment ago, is our what we call Task Order 2 Astrobotic. It's their Peregrine 1 lander, and you can see the different instruments that we have on board. And one of the things that I wanted to show within the manifest for these first 2 missions, because they didn't necessarily get the science that they were aiming for, we, in some cases, got different science that we didn't expect to get that is also helping us to better understand the environment in cislunar space as well as the environment on the moon. So for...
Can you tilt the microphone up? So yeah, perfect. Thank you. Just so we can all hear you. Thank you.
Sure. Is this better?
Yes.
Fantastic.
Thank you.
Okay. Sorry, I'm used to just not having a microphone in class from my past life as a professor, and not as used to the microphone. Okay, so the manifest here you can see has a suite of instruments. LRA is the laser retroreflector array. This was on board both the first and second missions that we have launched this year. And that is a great way to create lunar fiducial markers on the moon so that future spacecraft that are coming in can use those as place markers for known positions on the moon. And then, as Dan mentioned earlier, we had a couple of different instruments that looked at the radiation environment, and they were able to get data in cislunar space during transit observations, both LETS and NSS. I will let you all read the lengthy names that are very good at describing what the goals are for the individual instruments. And the NERVIS and PITMs are both designed for understanding volatiles. They were aiming for understanding the environment on descent to the moon, as well as our nervous PI keeps saying, looking at the dirt and trying to figure out what the dirt is all about on the moon. So these instruments, because we did not go to the surface of the moon to look at the dirt instead, they played a really great role at understanding what the environment around the lander is or was after the valve failure occurred, so that we could help with our instruments to help diagnose what had happened with the lander. So I feel like this is a really good example of just because your payload is designed to look at dirt doesn't mean that you can't also collaboratively help with troubleshooting and figuring out what's going on en route to the moon. So that was a really exciting thing for the payload teams to be able to get data. They all did get some data in transit. And as Dan mentioned, we do believe that we have enough data for our payloads to publish their data. And then the last one that we have on here is NDL, and I have this in a slightly different color because it is an instrument that was developed by NASA, but instead of it being a CLIPS payload that was manifested, instead it was used in line with the spacecraft as their primary method for navigation to the surface. That payload is also near and dear to my heart because it is also on the second NASA CLIPS manifest with Intuitive Machines, and we did get excellent data with NDL on that mission en route to the surface of the moon. So the second task order that I'm talking about, we affectionately call Task Order 2 Intuitive Machines. It is their first IM-1 mission is how they refer to it, and it's the Odysseus lander. This was a lander that went to the South Pole region of the moon, about 80 degrees south. It is the furthest south that we've had a soft landing with a lander to take data. You can see the suite of payloads here involves both technology goals as well as science goals. So moon to earth communications node, again, the fiducial markers, and then in addition, we had technology demonstration so that we could measure how much propellant we had in the tanks throughout tanking, as well as before and after maneuvers en route to the moon and on descent. So I really love the fact that even though we did not settle down in perfect orientation, that all of our payloads were able to take some level of data. It ranged from transit checkout, surface checkout to understand how the Scout's payload was able to take data. They did not get the science data that they were aiming for, but they are manifested on the next mission. So we're hoping to get that. But the others were able to get data that will be useful science data, and they're all very excited about the data that they've gotten. So that's Intuitive Machines 1. And I want to point out, because one of the common questions is whether or not there is a common theme amongst the NASA payloads. And for PM1, investigating volatiles and studying the radiation environment is kind of an overall science technology theme. For the IM1 payloads, as opposed to PM1, they were testing technologies that really help us to pave the way to autonomously and safely land on the surface. And then common to both landers, as well as the other manifests that we have in general, is trying to understand both how to get to the moon safely, as well as how to live and work safely on the moon. So understanding the environment on the moon, as well as in transit, for paving the way for the Artemis missions is really key for CLIPS as one of the base programs, I guess, really it's an initiative, is how we refer to it, for the Artemis project. So I think at this point, I will move on to Trent. I do have some slides that talk about the manifest for IM1, or sorry, for the Blue Ghost lander as well as IM2. And if we get to it, we can pop back to those slides.
I'm not building a lunar grid, but the down slides are not working for me. And now we're back to the beginning. Can you guys help? In the back?
They're working it in the back.
Okay. Good afternoon. I'm Trent Martin. I'm the Senior Vice President of Space Systems for Intuitive Machines. I also served as one of the mission directors on our IM1 mission, so I can talk quite a bit about the mission that we just completed. The CLIPS program is an incredible program that allows us to do science at a very, very low cost. These missions cost around $100 million a piece, give or take. And to do that, which includes the launch costs, is pretty incredible. So the fact that we have two companies sitting here on the panel that have successfully launched and attempted missions is profound. But I also might say that there is a healthy bit of competition. Despite the fact that that Astrobotics launched before us, I still would have beat them to the moon. And I just want you to know that, Dan. Okay, so looks like we have things working. So we have developed a complete space program, not just lunar landers. We developed a capability that allows us to not only put landers, but also provide communications and data services to and from the moon. You can see here the Nova C Odysseus lander as we shipped it from Houston to the Cape, and then you can see it here inside of the Falcon 9 fairing. In addition to building and testing our lander systems, of course, we have to meet all of the qualifications as required by the launch vehicle, as well as the agencies like the FCC and the FAA for licensing for our vehicles. We were able to successfully provide for launch and transit. We do have a liquid oxygen, liquid methane system. That's the first time ever that anyone has used a liquid oxygen, liquid methane outside of Earth orbit. And in fact, no propulsion system like this had ever been used in space. We were able to use it all the way to the surface, and it worked great. We successfully demonstrated that our fully loaded Nova C class lunar lander could be launched, and in fact filled at the pad. We filled at the pad and finished filling just a few minutes before launch. We successfully validated, implemented our innovative tank and structural configuration. We used a COPV Type 5, so a linerless tank for our prop system. We build all of our own propulsion systems and test in Houston. We knew that it was going to work because we tested it on the vehicle, on the flight vehicle, before we took it out and launched it. We successfully validated our radios and communication links. We use a system that we call our Lunar Data Network, which is independent of the Deep Space Network, intentionally because we realize the DSN will be overwhelmed with the amount of data that we're getting from upcoming satellites that NASA is working on. So we built our own Lunar Data Network, and we offer that as a service to people as part of our system. We validated our proprietary liquid methane engine, as I talked about, in deep space, and actually all the way down to the surface of the moon. I will point out that our operations approach is slightly different than what you will see in a traditional NASA mission. We intentionally were trying to go as lean as possible. This is our control room. It is only has 10 people in it. Although we do have back rooms that support these folks, our goal is to minimize the operations down to just the bare minimum that is required. Obviously, that changes as you go through the mission, as you go from launch and operations to the surface. It changes once you get on the surface, and we validated that approach during this mission. This is landing. You can see in this image, this is taken right as we are touching down. If you look closely, you can actually see the movement of the rocks and regolith as it's being blown out of the way as we're landing. Unfortunately, you can also see one of our landing gear off to the side. We did come down. Unfortunately, we had an error in our LiDAR, our laser altimeter system, that we didn't get them hooked up properly. We attempted to ingest the navigation Doppler LiDAR system into our GNSC system and almost got there. We had one flag that didn't quite get there. So that meant that we ended up landing a little bit harder than we anticipated. We discussed that in our post-mission briefings, but essentially we landed about 3 meters per second down. We were intending to be about 1 meter per second down and 1 meter per second to the side, and we intended that to be 0. That meant that we broke off one of our landing gear, possibly 2, on landing. So we ended up falling to the side around 30 degrees. But even with that, we were able to complete the landing softly at the furthest south location that anyone has ever done, any company or country. We are the first company to have ever successfully soft landed on the surface of the moon. And we believe that this is just the beginning of what CLIPS is going to do for the science community. We delivered all of the data that was required of us on the surface of the moon. We were required to do 144 hours of data from the surface. We actually did about 157 hours of data from the surface. We delivered about 1.7 gigabytes of total data, around 550 megabytes of data from the surface. The scientific instruments that we had on board Odysseus were not really data heavy. So delivering data back, despite the fact that we had turned on our side and we're not using our high gain antenna, we were able to still get data back from every single one of the science instruments that we had delivered to the surface. Obviously, if we land with the high gain antenna pointed at the surface, at the Earth, we can get much, much higher data rates. And we proved that with our Lunar Data Network operationally during the mission. The other thing that we did was we were able to actually coordinate with DSN and get comparison data between what we had with DSN as well as with our Lunar Data Network. With that, I will stop there and move on back to Joel for questions.
Thank you, Trent, and Sue and Dan. So you're hearing from 3 individuals whose organizations were involved in 2024 with attempting to go to the moon and land on the surface and conduct operations. Let me ask a general question to the panel members. So we're all familiar when the United States went to the surface of the moon in the 1960s. We landed with small robotic surveyor landers from 1966 to 1968, and then we landed human explorers from 1969 to 1972. How do you think landing on the moon and doing science on the surface of the moon will be different in the years coming up compared to what people are used to thinking about from the history of Apollo?
I guess we don't need a clicker.
Nope.
Why don't you start?
So I think this is an excellent question. Clearly, we keep talking about how it's the first time that we've soft landed on the moon in over 50 years from the United States, that is. For us, it's very exciting. The changes in the technology that have happened between the 60s and 70s and today, I think everybody can probably agree, are pretty astounding. What that means is that the kind of data that we can send back is going to be very different. We're going to be able to challenge ourselves with the potential high data rates that we would want to have coming back with future instrumentation, with cameras that have really high resolution images, the kinds of science that you can get when you start doing things like bringing mass spectrometers and thermal infrared instruments and things that, especially for us moving forward into creating a sustainable future for the Artemis astronauts to live and work safely, it means creating technologies that are very different from what we had in the past, right? So we start with, imagining what it is that we do for individuals that go to the moon for a matter of hours or days. And it's kind of like preparing to go on a journey across seas with one suitcase. And then you turn it into, okay, but how is that different if I need to move there? It might be that you can pack up enough food and you don't need to take pots and pans along with you to figure out how to live and work there permanently. It might be that you can, take sponge baths on the way, but if you're going to live and work on the surface, it's probably going to be a different kind of environment that you want to create. So that means that we need to also understand things like when the Apollo astronauts went, one of the things that they really learned was the dust that got into their suits was very, very difficult to deal with. And so the CLIPS instruments are very largely focused, especially on the next mission that's being launched with Firefly, on understanding that dust and understanding how to mitigate and remediate the effects so that we can have the astronauts live and work safely on the moon. So I think it's that combination of trying to figure out how you live there more permanently with the new technologies, as well as using the technologies before we get there to make sure that we are really understanding what kind of environment we need to prepare our astronauts to live and work safely.
I would say the biggest thing that I would point to is at the end of the Apollo program, the moon was a desolate place. It is no longer a desolate place. We now know that there is at least water ice at the poles. The scientific endeavors that we intend to look at are how do we get to that? How do we get those resources? How do we utilize those resources? And a lot of the science that I'm seeing is focused around that, focused around finding and potentially utilizing those resources.
Yeah, I would say location is one of the differences. You know, we had all those Apollo missions at the mid-latitude region, and now the poles are becoming accessible so we can get to that water ice, as Trent's pointing out. That's a really remarkable change. The other thing that I think a lot about is repeatability. So the ability to send the same instrument multiple times. On our mission, you know, we had instruments that maybe didn't get the data that they were expecting from the surface, but as we talked about, they were able to be turned on, they were able to understand their ConOps, get a higher TRL for their instrument itself. And I think that then feeds forward to the next mission. There's many lessons learned so they can utilize that instrument again and again in the future. And that repeatability just really didn't exist in the sense of CLPS missions can do it over and over and over. And that it seems like a really empowering new paradigm for science.
So another thing that we think might be different in the future than what we observed in the past is that we're used to thinking about sending robotic explorers to destinations and human explorers. But and of course we remember Apollo mostly for watching the astronaut explorers maybe doing field geology or placing scientific instruments on the surface. Now you've all just recently been involved sending robotic explorers to the moon. How do you think the future will be different? What will the combination or synergy be between human explorers and robotic explorers in the future?
Yeah, just as we've seen the use of robots in daily life on Earth, I think we'll see the same thing in space. You'll be able to utilize robotic explorers, robotic rovers, robotic hoppers, which we're launching on our second mission, that are used in conjunction with human activity. If you go up to the edge of the Shackleton crater, it's 6 kilometers deep. You're not just going to jump down inside. Maybe you send a hopper down inside to do some scientific research that you're interested in before you send the humans down inside. So I think you'll see it in combination.
Yeah, I might add, I mean, similarly, we have a cube rover, so it's a small wheel-based mobility system. It's a rover. And with that platform, I think what's exciting is having the same platform used over and over again. So we can use it on a CLPS mission and provide science data, but then those cube rovers could also be companion robots for future astronauts. So literally the same vehicle that was designed for a science mission could one day be alongside as a companion vehicle for an astronaut carrying tools, driving ahead, looking for hazards, and ultimately be able to work alongside the astronaut. So I think what's so exciting is you have commercially minded thinking that's helping to reuse the same platforms without significant non-recurring engineering occurring between missions. And I think that's an opportunity for the human and robotic side to work together.
Now, again, when we talk about going to the lunar surface, we naturally think of Apollo, or we think about robotic Soviet probes, or more recently probes from the People's Republic of China. But in the United States, you know, it's been a long time since we've sent, until this year, robot explorers to the moon and preparing for human explorers to go back. And you know, during that time, for 30 years, we flew the space shuttle. We constructed with international partners the International Space Station, which is still in use today. And on that station, we've had permanent human presence for more than a decade. And now, although we always think about the lunar surface, particularly in this panel, as we go further out to the moon, we're going to be assembling a waypoint called Gateway in cislunar space. How do you all think that the lunar surface will be used with all of that experience, all that history of what we've accomplished in space and in planning to go back from the moon? How is that really, do you think, going to be affecting what we do on the surface of the moon?
For all of you graduate students out there who are planning for, preparing for defending your thesis, consider some of the questions that Joel asks. So I think that's a very excellent question. As we mentioned earlier, and Trent mentioned earlier, when Apollo went to the moon, the Apollo astronauts, it was to go for a very short amount of time. And when they left, it's been 50 years plus since people have walked on the surface of the moon. With the plans that we have now, the plan is to go back in a more sustainable way, where we have a way for the astronauts to come up and down to the surface of the moon. We have a way for them to live longer term. And I think that with us people, in a general sense, it doesn't matter what country you're from, imagining exploring beyond the Earth is something that inspires the next generation. It inspires innovation, and it allows us to work together collaboratively, whether it be government, commercial, international partners. And when you have a common goal that's for the betterment of humanity, like living and working on the moon, that presents all the challenges that require all of the entities to get together and work together cooperatively, I think that really helps for developing humanity's capabilities in the future, not just on the moon, but then how those technologies can spin off and help us here on the Earth as well.
I think you have to look at international collaborations, international partnerships, international business that is occurring. I know Astrobotics as well as Intuitive Machines have both sold missions, payloads, to international space agencies, other space agencies that are interested in going to the moon but don't want to set up an entire program to build landers. They want to do science on the moon, and they're willing to do that. I have a fourth mission that we've already potted with a space agency, specifically buying about 20% of that mission. So that is already occurring, and it's occurring because of this new paradigm, because of the ability to have commercial partners in the mix. And it's not just the US government. You know, Apollo, we spent 4% of the US budget for 10 years to put astronauts on the surface of the moon. That's a huge amount of money. We can't just assume that that's what we're going to do for the future. That's not how it's going to work. It's going to have to work in a different way. And I think Space Shuttle and Space Station have led us down this path of our partners throughout the world. We can partner with those folks, and we can find ways to do things together, spreading the cost across multiple governments.
Yeah, I would just add, I think part of the reason that the ISS has been a successful and enduring project has been that international involvement. And so what missions like ours offer is an opportunity where there's trains that are leaving the station on a regular basis, which provides an on-ramp for these agencies that historically would have never thought about participating on a lunar mission unless it was a large contribution. There's a possibility to have much more modestly sized payloads that work very well with the CLPS missions in particular. And so I think we serve as an ability for those agencies to join these missions and then ultimately join the entire Artemis enterprise.
Let me ask a question first to Dan and then to Trent. So Dan, you outlined to the group here about what happened on Peregrine Mission 1. Apart from the propulsion anomaly, what was the biggest surprise that you think you saw out of Peregrine Mission 1?
I think in some respects, we had intended to land on the moon, so that was obviously the unfortunate thing, surprise in a sense. But the really uplifting surprise was just seeing all of the payloads getting data, turning on, and the entire team rising to the occasion. Not that I'm surprised that our team rise to the occasion, but just the joint teams between the payloads and the lander team working together to still get a variety of successes that weren't planned, but still gave us really valuable practical experience that will feed forward to future missions. and ultimately still get science. I'm so proud of the science team still getting usable science. That's just such a win, given that many of them thought that they were not going to be on console for until 30 days after launch. We were planning for basically having the payloads in more of a stasis in a sense, and as far as the mode was concerned. And so the fact that they rallied immediately after the anomaly occurred was just a really heartening and exciting development to see in light of some circumstances that we were not planning for.
Same question. So we built an incredible vehicle, and we learned how to fly it for the first time over a 6-7 day period as we flew to the moon. We knew going into our launch that Astrobotics had the failure that they had, and NASA came and asked us, how do we know that you're not going to have the same failure? And I said, I can guarantee I won't have that failure, but I'll have something that goes wrong. That's just part of space missions. Things go wrong. You can't have everything go right. We had other things go wrong, and we learned from each one of those. Fortunately for us, we got all the way to the surface, and that allows us to take those lessons learned, build those into our next mission. The next 2 missions that we have are also on the Falcon 9 with the Nova C. So it's the exact same repeated technologies that we're flying, and because of that, we'll be able to roll those lessons learned into the next couple of missions and be much more successful than we already were.
Let's go to see if any of the folks attending the session have any questions. Jim, I've got a set of other questions I'm prepared to ask the panelists, but I'd like to see if anyone here has questions.
You've got one right there in the middle, so come on down. Keep your hand up. There you go. Coming from the other side, coming from the left.
All right.
There you go.
Thank you.
Thank you. I'm Daniel from the University of Rhode Island. The question I had is, for sustainability purposes, is anything being done, and if not, what would be done to prevent trash and garbage buildup on the moon and even Mars with the new efforts with both private and government enterprises?
I'll give part of an answer to that. Yes, sustainability from the point of view of either making things long-lived and affordable, but also not adversely affecting the environments that we're going into is on everyone's mind. I would say that the moon is a big place, and I think there are some places on the moon that special attention is going to be paid to. Parochially, I'll tell you that the United States, for example, really doesn't want anyone disturbing what we consider historic sites on the moon. I'm sure other nations feel the same way about their historic sites. Several of the panelists mentioned that there is a desire to understand if ice water exists on the moon. Some people look at that because they like to exploit it. Other people are interested because they want to be able to do scientific studies of it and look at how volatiles such as water came to the Earth-Moon system. So the moon might be a laboratory that contains that information. As you can imagine, those might be in conflict eventually. So there are various groups that are looking at how do you enable people to do the work they want to do at the moon, whether that's business or technology or science, but not in effect pollute or change the areas that you're working in. So let me turn over to the other panel members.
I will say that we spend a huge amount of our time answering questions just like that from NASA, in particular around orbital debris around the moon, looking at trajectories of our vehicles compared to other vehicles around the moon to make sure that we don't have collisions. Separately, looking at our vehicle once it gets to the surface, what volatiles do we have coming off of our vehicles? What happens with those volatiles as they evolve? What happens to our vehicle at end of life? How do we ensure that it doesn't create some additional hazards to minimize the footprint that we're creating?
Yeah, I would add, it's a topic top of mind for us, as evidenced by the fact that I think our mission could have gone many days longer had we not decided to do a controlled reentry. In fact, we believe we probably it might have been a stretch, but we may have been able to even attempt an entry into lunar orbit. But because we cared so much about the cislunar environment and maintaining it, that's why we decided to end our mission when we did. I'd also add, I think, as we look ahead to future architectures like Lunar, those are systems that I think directly correlate to sustainability in the sense that if you have vehicles that can operate for months, years, maybe even indefinitely, that inherently reduces the number of vehicles that you're sending over and over and over. And so that's why we're big fans of having a lunar power grid, which incidentally also sort of centralizes your activity. So if you have the grid and you have the Artemis Base Camp in one location, inherently that sort of concentrates where you have your activities, which then I think speaks to what Joel was talking about, having specialized areas of the moon that certain areas may be more pristine and left alone versus others.
Yeah, and I would add to what Trent was mentioning earlier. In my past life, one of my past lives, I worked with the Orbital Debris Program Office. And I remember hearing when I first started about how back in the 1950s, they talked about, what are you going to do with the spacecraft once it's done? And the answer, well, space is large, so it's not a problem. We're not going to worry about it. And I think that the viewpoints that we have now are very, very different from what we as a human race had back in the 1950s. So there are entities at NASA that are very, very serious about making sure that we do have conjunction analyses that are done for the spacecraft for just this reason, to ensure that the environment around the lunar orbits do remain pristine. We do not have the luxury of junking up the lunar orbit like we have with the Earth, because with the Earth, if there's a problem where there's a potential conjunction with the space station, of course, the astronauts go into the Soyuz and they can immediately, disembark from the space station and come back to Earth within hours. If we're at the moon, we do not have that kind of time luxury. So at least throughout the mission with I worked directly as well with the people at NASA who do those conjunction analyses, and they were also very good stewards of space, just as Astrobotic was, in ensuring that we had the necessary trajectories so that the conjunction analyses could be done, so that if there was any potential threat, that they were prepared to make sure that their orbits were altered to prevent a collision from happening. So we're all very, very well aware of it. It's a great question.
Okay. Yeah, I have the mic. Hi. I had a question about the human landing systems. My understanding is that both SpaceX and Blue Origin are going to land an uncrewed vehicle as part of their test program. Is there much talk about putting some of these instruments or putting other instruments on those and using those vehicles as just to carry payload or carry instruments to the moon?
You're correct that both of those companies will have unpiloted, uncrewed landings to test their systems. I believe they'll each have at least one. Yes, there are discussions about putting scientific instruments or technological instruments on those uncrewed landings. I will point out that those uncrewed landings are flight tests to test their vehicles. And in some case, and of course, they're going to have to focus on getting their vehicle data out of those landings. So any scientific or technological instruments would be secondary to that.
You got several over here. Pick one, I guess. Yep.
So, hey Trent, my question is going to be for you mainly here. I'm from the University of Illinois. So my question was mainly going to be that with the recent novelty and popularity of Methalox engines specifically, and given that most of them are used on first stages, and given that you guys are probably the only company that's used them in deep space. So far, I was going to ask what kind of lessons learned or what kind of unexpected challenges did you guys have with Methalox when landing on the moon? And would you be able to further elaborate on generally just Methalox specifically in deep space?
Yes, we specifically chose Methalox for deep space because we believe it is the future. It's a shirt sleeve environment test is all that's required. We test in our facilities in Houston, and literally within seconds we'll walk out and we'll look at the injector to see if we can see any ice buildup on the injector. You can't do that with a hydrazine engine. The byproduct is essentially water, right? So it's a very clean burning it's a very efficient technology. We didn't use pumps on our system. We used a pressure-fed system. It was very, very easy to build and certify. It worked perfectly. We flew it with COPV Type 5s, which first time ever that's been done as well to reduce the weight. And we believe it is the future, not only for the moon. Yes, I can create water, and with the carbon bed, I could create some methane. But for Mars, where methane is a ready resource, we see a Methalox engine as like the Conestoga wagon of the future space missions. And in fact, when a lot of my team worked at NASA Johnson Space Center on a program called Morpheus. Morpheus flew a bunch of missions and a bunch of flights, the terrestrial flights, one of which actually crashed. They dug the engine out of the dirt, cleaned it off, and used it on the next mission. So it's a very robust technology.
We have another one over there on the far right.
Hey, thanks for the discussion today. I think Odysseus was really impressive because it was able to, switch to a contingency plan, maybe one that was not originally planned. But I'm really curious what sorts of lessons you can learn from this. Like, are there plans to add any redundancy to GNC for future missions?
So I would say that all of the CLIPS vendors are very specific on what risks we choose to take. And redundancy is one of those where we choose specifically where we're going to have redundancy. I know on our systems we have redundant comm systems. I have 4 radios, 5 different antennas, 2 different types of radios. I have 2 different types of IMUs. I have 2 different navigation pods. And I have 2 laser altimeters. Turns out if you don't hook up either one of them the right way, they don't do you any good. But what we did learn was that we have an incredible team that was able to, in a very, very short period of time, realize, 1, we have an issue. 2, we have a potential solution if we utilize this payload that we have sitting here. And we were able to actually take the laser altimeter measurements out of the NDL, pipe them right into our GNC system in a matter of hours, reorient the laser for the NDL relative to where our lasers would have been. And we know that the data actually was ingested into our GNC system. Unfortunately, upstream of that, we had another flag that said, hey, if this laser altimeter isn't telling you that it's good, ignore all the data that's coming into that pipe. So given a 2-month, 3-month period to go write new software and write all that, it would have been great. When you only had 3 hours to do it, it was real time, we missed that one flag. If we had to do it again right now and I had those laser altimeters hooked up correctly, I would fly it exactly like I just flew it.
Yeah, I can also tell you that I've seen the NDL data that he's talking about that our NASA CLIPS payload had, and it looks good. I wish that I could have showed you the data here today. I was pretty excited when I saw the data. And that also is a really good note that just because it didn't land in an optimal way doesn't mean that all of our payloads didn't get data. In fact, they all got some data. The NDL data was the data that they were hoping for to be able to understand the trajectory coming down. The RFMG got what they were looking for. LN1, our navigation instrument as well, had 4 passes on the way to the moon, and they got additional data, 2-way ranging with the DSN that we didn't expect to get. Our Rolls' payload had an antenna deploy in transit, so we ended up getting data in transit that we didn't expect to get as well. So for the contingency type planning outside of the lander itself, it was really fun and exciting working the actual mission, being on console, working with the different payloads to try to figure out what we could get. And I think there was a quote, and I don't remember exactly what it was, but the gist of it yesterday, somebody can probably clarify, was, planning is irrelevant, or the plans that you make are irrelevant. It's the planning that is really what matters in the end. So all the preparation that we did for how the payloads were going to operate allowed us to be very agile in figuring out what we could get instead of what we necessarily were ultimately aiming for. It was great.
Got one over here on your left.
Yeah, I had a question for Trent and for Dan. The question for Trent was, do you anticipate IM-1 to reestablish communication after the lunar night, similar to the SLIM robot? And then for Dan, I was wondering if you guys are also thinking about developing your own communication network like the LDN, or if you guys intend on using an alternative.
So, all right, so about 10 o'clock yesterday, Wednesday in Eastern time, the sun had risen high enough up that we should have been producing power on Odysseus. We have been listening since then, and we will continue to listen. We turned the vehicle into a quiet mode, essentially, when we turned it off in February, and so it should come back up and be talking to us if it's going to come back up. I think it's highly unlikely that it will, but there is a possibility, and we will listen out for the next couple of days and just see what we hear. And then before Dan answers his question, I would gladly sell him that service if he's interested in it.
Well, that sort of relates to my answer. We're not looking to develop that internally. We're going to use commercial partners. So send me your price list. Got it.
Hi. Thank you so much for being here. It's a very exciting panel. It's been fun watching all of you over the last couple of years and being here today to talk about the missions that's happened. My question is about the risks and opportunities for comms around the cislunar environment. Specifically, I was thinking about the previous panel with digital twins, AI, ML support for astronauts when they're out there working, and just would like to get your opinion.
Opinion on using digital twins for
Your comms network, would it be able to support that? That's a lot of data.
Yeah, so there's very limited capability in cislunar space right now. Very, very limited, right? So you're not using GPS to help you navigate. There is no system that exists. NASA does have the Near Space Network Services contract that is out there and in work now, and hopefully will be awarded soon. The idea is that there would be some capability that not only provides some level of communication, but also position, navigation, and tracking in lunar orbit. Yes, if you had that system in place, digital twins would be a very helpful tool. And in fact, we utilize something very similar to that. We are planning what we call Constellation, K-H-O-N, the Egyptian god of the moon, and where we will put satellites around the moon in order to augment our LDN so that we can get not only dishes on the Earth, but also a communication relay network and position navigation and timing and telemetry around the moon as well. But yes, in the future, but not yet.
We also need to figure out how to become the weather gods, because as it turns out, no matter how good your comms are on the moon, it might just depend on the winds in Australia and the rains at Goonhilly, which is a book that Trent is going to write after the IM-1 mission is over.
Yeah, there were a few times where the wind would get too high at Parkes and at the Parkes dish in Australia, and they had to park the dish, and that would drive data for that day, simply because the winds were too high. So you get the winter. The summertime in Australia, the winds get high, and unfortunately they park the dish a lot. It's a 64-meter dish. If you really think about it, that's 3/4 the size of a football field. Not surprising that the winds might cause it to move.
We have one more back here. Well, congratulations to my colleagues for both the accomplishment of setting CLIPS in motion, Joel, and for your two teams, Astrobotic and Intuitive Machines. Great work. Two questions. One, and I think you picked on it a little bit, Trent, so maybe Dan can answer it. What else is missing to be successful? Because you're just starting, you're blazing a trail. You talked about a few things that are missing. The second is, and that goes to Trent, how close did you land to where you thought you were going to land?
Yeah, so I guess to answer your question, I might actually take a different route than maybe what you're expecting. You might be speaking into like capabilities. I think one of the things that we're really excited about is kind of the evolution of the CLIPS program. So in the future, we're hoping that we'll see eventually block buys of lunar missions, which we think will be helpful because there won't be sort of one-off missions, but rather the ability to then really line up your supply chain. You can plan out with your payload customers about multiple missions. Sometimes we have the challenge in this market of payload customers that want to know, do you have your payload or your CLPS task order locked in yet? And then when you tell them that you have, they say, well, it's too soon now for me. So I think one of the things that I'm really looking forward to is a sort of a map of, or schedule, I guess would be a better way to put it, of missions that are running on a multi-year scale, which I think will help the market to develop. And I think that's one of the things that we're most excited about from a programmatic perspective to help build out these capabilities and help build out the capability of the market in general.
So our final landing site was in a crater near our final expected landing site. We were about 1.5 kilometers away from the ellipse that we were targeting. Given that we didn't have a laser altimeter, we couldn't actually tell how high we were. We were operating purely on DPAS and IMU. We think that's pretty darn good. With laser altimeter, we envision that we can easily get within the 100-meter circle that we're trying to get, and probably closer to 50 meter to a designated target.
I think we'll take one more, as long as it's a quick question.
Yeah, I've got it here. Hey, Quint Duden, Space Logistics. Thanks for being here today. I've enjoyed it very much. My question's a little bit broad. I've been trying to trim it down in my mind and give you a little preamble. I look at China's program, the CLEP program, and their director, who's an astrogeologist, and it's clear to me their whole mission is in situ resourcing. Our mission is persistent existence. That's got to bring challenges that are different. Have we gotten any lift? I know they embargo their stuff by large part, but looking at their program compared to ours, they're interested in the same area we're interested in, the South Pole. What are your thoughts on that in general, and how do you think that'll play out if you've had those thoughts?
I think certainly we're excited for the international community to participate in lunar exploration, science, and commerce. But I think what that points out is the very critical need for the U.S. to get to the surface, to have not just the Artemis missions, but also commercial missions at the surface, and have presence that is enduring, so that things like behavioral norms are being set by those that are participating and that are there. So I think it just highlights the critical need for the U.S. to continue the momentum of the program that it has going, and to make sure that there's a presence so that, as I said, the normative behaviors are not set by someone else ultimately.
There's a lunar space race going on, and we all have to recognize that it exists, and we need to be, as a country, we need to be making sure that we are in the game.
I'd also say that when you compete, you want to play to your strengths. What we have in the United States is we have a vibrant, entrepreneurial, innovative group of private industry people. We have long-term investment by the public in exploring space. We have some of the best scientists in the world. We watch and we see what our competitors are doing. I mean, for say Chinese researchers, it's really good they publish a lot of the same journals that we publish in, right? Our scientific results. We have worked over several years to bring more and more partners into the framework we call the Artemis Accords, to set kind of cultural and almost business norms of behavior. One of those norms that we promulgate is that we want to make sure that no one is denied right of access to areas of other bodies. So no matter what people are doing on Earth, we want to make sure that any individual's organization's right to get access to a body under the Outer Space Treaty is not denied by anybody.
Okay. Excellent. Any closing comments or anything?
I want to thank AAS for having us at this panel to talk about lunar surface science. I want to thank all of you who stayed for the last session of the day. Thank you very much. And I want to thank all the panel members, Dan from Astrobotics, Sue from NASA, JSC, and Trent from Intuitive Machines. Thanks so much.
Yes, thank you all very much. Thank you.